We are going to continue our discussion of potential energy diagrams towards SN1 and SN2 reactions. And we have 3 questions to answer. What would happen to the rate of the SN1 reaction if a polar product solvent was used? Here's the hint. Polar product solvents stabilize carbocations. This morning, we went over the list of all the solvents and the nucleophiles. We're going to, after this video is over, we're going to look at this morning what we did. All you need is this fact from this morning. Polar product solvents stabilize carbocation. So the energy of the carbocation is going to be lower after you add the solvent okay, and that also lowers the hill. So everything comes down. Everything comes down. All right, and here's your new cation. It's the same cation. I'm squeezing it in here, except I'm going to show that it's been stabilized with something like an alcohol that has a lone pair on the O. Alcohol, solvent. Lone pair is stabilizing the cation. You see that interaction there? I put little dots, like a partial bond kind of dot thing. Is that what it looks like? I hope so, because that's what it is. And that brought the energy down. And most importantly, it basically, it's like you grabbed the bottom of this hill with your hand and did this to it. That brings the tops down too, right? Just pretend that's a piece of wire up there. If you're going to yank down this thing, everything gets yanked down with it. So blue is after the solvent's added and black was before. Got it? What happened to the rate of the EA here? You now only have to go to this height. The lower EA did what to the speed of the reaction? The speed of the reaction, not the height of EA. Remember, the bigger the EA, the slower the reaction. Blue is lower than black. It's faster in blue. So answer, very similar, very short, in words only. Answer. Lowering EA for RDS speeds up the reaction. There's your answer. Scribble that somewhere on your old activity. That's number 1. And we'll use color coding for 2 and 3. We'll change that to green. Polar A product solvent was used, which stabilizes the transition state. Well, if you're stabilizing the transition state, means you're lowering the energy of this hill. You're only talking the top of the hill this time. You're pushing down the top of the hill. Stabilized by polar A product solvent. Okay, so when you did the polar A product solvent, the hill's now smaller. So the answer to question 2, reaction speeds up. Don't forget which reaction you're talking about. SN2. A polar A product solvent will speed up an SN2. A polar product solvent, like an alcohol, which reaction does that speed up? This is what you have to learn, people. The alcohol sped up which reaction? Do you need to see the labels at the top? The alcohol sped up this reaction. It did not help the other reaction. The polar A product solvent sped up this reaction. I'll give you a diagram. You do not have to copy it. Here's a diagram of a transition state between cyanide reacting to make a bond to the carbon that has these three things, and then the X is leaving. It's leaving as a minus. Cyanide started minus. This is the transition state. This is just an aside. You do not have to copy it. And the transition state, there's no cation, so we got R, we have, I don't know, at least one H, and then R prime. Okay? So what happens is you'll have a polar A product solvent example, acetone. The bonus on our last test. Here's what acetone does. It sneaks its, I don't know, we'll put a new color for acetone. I don't want green anymore. The O sits out here because it's, oh, that's no good. The carbon sits out there. Why? Because that puts a delta plus near a delta minus, right? What's going to happen to the stability of this when you have a slightly positive near it? It's going to go up or down. You're going to get happier or more happier or less happy. Happier. When charges are opposite, things get more stable. Similarly, on the other side, the acetones down here, helping out, same story, delta plus is near delta minus. That's an attraction. That's an attraction, okay? So we're stabilizing the SN2 transition state, TS with polar A product solvent. There's a much prettier diagram in the textbook if you want it, okay? You didn't need to copy that. Question 2 is answered. It's in green. Question 3 will be in, I don't know, light pink. Oops. Highlight it first, then change its color. There we go. What would happen to the rate of the reaction if a stronger nucleophile was used? Stronger means less. Oh, I didn't write the word stable. Thought I said it. So in pink, if nucleophile is less stable, that does that what to the reactant starting energy? Higher or lower? If it's less, what's it say? Less stable. Up or down? Potential energy diagrams. Stable, unstable, more stable. Where are you the most stable? When you're lying down on the ground, right? When are you the least stable? When you're jumped up 5 feet in the air. Oh, good luck with that. That's good athletics, by the way. Okay. So yeah, when you're lying down flat on the ground, that's as low as you can go, right? That's the most stable you can be, right? You remember that? Okay. So here's the diagram. If you start out with Rx plus nucleophile, and the nucleophile is less stable. How do you know it's less stable based on question 3? It says it's more reactive. What's a synonym for more reactive? I just wrote it. Less stable. This does not change the top of the hill. It's the same transition state you have to get to. So you didn't drag it out down or push it up with this thing. So you're starting from the pink to the top of the hill compared to starting with the black to the top of the hill. Which one's faster? The upper one, that's right. Answer to question 3 is right here. EA pink, EA is lower, with stronger nu. Therefore, faster reaction. I will stop the share and circle the things you got to write down.